Well, I thought I'd tie up some loose ends in the discussion about the proof of the Riemann mapping theorem and explain what I would mean if I said the Riemann map. And answer any questions you might have. The take-home exam will come out after class. I'll put it on the home page, and also it'll be posted in Gradescope. So I thought I'd do a little bit of review today, too, before that happens. Any questions about anything? Let's see. One of the loose ends I left unfinished was in the unbounded case of a simply connected domain that's not the whole complex plane, I need to show that there exists a one-to-one map into the unit disk that's analytic. It's kind of a technical point. It's not going to be hard, but it's an interesting thing to think about. Stein does it in a different way than I'm going to do it. I think my way is easier. Okay, so I mentioned this last time. Of course, if omega is the whole complex plane, then Liouville's would say any analytic function mapping into the unit disk would be constant. So that certainly the Riemann mapping theorem is not valid when omega is the whole complex plane. But if omega is not the whole complex plane, is simply connected and bounded, then it's easy to cook up a one-to-one map. Then f of z equals z divided by whatever the big bound for that domain is, would be a one-to-one map. This is a one-to-one analytic map. Omega into the unit disk. It's not onto, probably not, unless omega is the unit disk. It's a disk of radius m. It's a one-to-one analytic map into the unit disk for big enough m. For big enough constant m. Okay, so that case is easy. And the case we're going to think about right now is the unbounded case. So it's going to be simply connected, unequal to the whole complex plane, and unbounded. Okay. Well, it's not. Here's how to cook up a one-to-one analytic function. Let's call it f that maps omega into the unit disk that's one-to-one and analytic. And this was so that that class of functions f is not empty in the proof of the Riemann mapping theorem. In particular, that number m that was the soup would exist and be a positive number. If that thing was empty, then the whole proof would break down because you wouldn't have anything. That m wouldn't even make any sense. So here's a fun thing to do. So this is how to do it. Omega is not the complex plane, so there would be a point in there. So there exists z naught in the complement. Okay, so z minus z naught is non-vanishing. It's non-vanishing on omega, which is simply connected. And we have a theorem about that. All those theorems we proved for the convex case using Cauchy theorem hold on simply connected domains because of the now fancier Cauchy theorem. So there exists a square root of z minus z naught that's analytic on omega. There exists, because it's non-vanishing, an analytic function g on omega, whose square is that thing, with g of z squared is equal to z minus z naught. Okay, I claim that g is 1-to-1 first. G is 1-to-1 on omega. And that's an easy thing to see. Let's see why. Because if g of z1 was equal to g of z2, then of course the square would be equal, and the square is something simple. Okay, so that would be equal to z1 minus z naught is equal to z2 minus z naught. And of course we get from that z1 equals z2. So sure enough, it is 1-to-1. That's my first claim. My second claim is that G misses a disk. G misses a disk on omega. I'll show you what I mean by that. Here's why. Here's one way to see why. Let's see. G is not constant, of course, because its square is not constant. Is not constant. So the open mapping theorem implies that there's a disk in the image. Open mapping theorem implies there exists a disk, could be small, disk of radius epsilon about W naught, let's say, that's contained in the image G of omega, because that would be an open set. Well, let's see. My next claim. Got too many claims going on. I guess I claim it. Sure, why not? Subclaim. The subclaim is that the disk minus d epsilon intersect with G omega is empty, where I'm making minus minus a set minus a set is equal to the set of minus z such that z is an S.
What is omega naught here again?
What?
What is omega naught here again?
Omega naught.
What W naught? Sorry.
W naught is just the center of that disk. G is not constant, so it sends omega to an open set, and so there is a disk. So there's an epsilon and a W naught, so that disk is contained in the image.
Okay.
That's the open mapping.
Okay.
Pick it. So I guess I should say pick any W naught you want in that set. The open mapping theorem implies there's a disk about it in there. Sorry, W naught could be any point in the image. I just need one though. So, okay, so that's my notation for the negative of a set in the complex plane. Let's see, why is that? I like to draw a picture for this. And here, well, I guess I'll say it first. Because G squared is 1-to-1. G of Z squared is Z minus Z naught. Of course, that's 1-to-1. Okay, so if that negative disk was in there, we would see that G squared is not 1-to-1. If d epsilon W naught and the minus of it in G of omega, then G squared can't be 1-to-1. And that's a contradiction. Okay, so that's why the subclaim is true. So the picture is, let's see. Here's how I like to think of, let's say my omega here is, I'll make a kind of like a branch cut. I like to make Z naught be this endpoint right there. But Z naught could be any old point in here. Remember, omega is simply connected, so there can't be any holes. So if Z naught is in the complement, it somehow has to get connected to the point at infinity. So it's kind of like a branch cut. Okay, so there's this is omega. And Z naught's in the complement. And so then I got this thing that's a square root. That's G. And G probably would open up that branch cut and be something like that. And that disk, this would be my d epsilon about W naught, and the minus of it would be over here. I should have copied it. This would be minus W naught epsilon. Okay, that's the picture. That's the picture. And now I've got a mapping that misses a disk. And we know how. And it's like what was that? The Cassarati-Weierstrass theorem. The next map I would take now, one that misses the disk, would be. Let's see, what would it be? Epsilon over Z minus W naught. So that would be a Z plus W naught. That would turn that inside out and to a bounded domain. That would map into the unit disk. So this would map into the unit disk. This would be 1, this would be 0. And it would take that blob. Let's see, it probably wouldn't hit 0, would it? Some blob in here. And that, of course, all those maps are 1-to-1. Is a 1-to-1 analytic map. The composition is, at least. Into the disk of radius 1 unit disk. So F is not empty in the proof of the Riemann mapping theorem. Questions about that? That's kind of an annoying technical point. It's not hard. It's kind of like the proof of the Cassarati-Weierstrass theorem when you use that disk that it missed. At least I got to use the open mapping theorem in an official way today. Haven't done very much with that, even though it's a very important theorem. Questions about the proof of the Riemann mapping theorem? Yeah.
Could you explain why the Z naught kind of like has this branch cut like thing?
Oh, because omega is simply connected. So if that's not in there, there can't be any holes. So whatever Z naught's in the complement, that hole has to sort of go out to infinity. I told you about this result in Alforce, that something is so that's just what I think of when I think of an unbounded, simply connected domain with a very small exterior. That theorem in Alforce, that being simply connected in the plane for a domain in the plane is equivalent to, in the extended complex plane, the complement being one piece. That means that Z naught would be connected to the point at infinity in the complement. Anyway, I don't want to get into that topology. This is just an example. You agree that's simply connected. Kind of like the branch cut for the log function. In fact, Stein uses a log function instead of a square function. But I think this is easier to understand. Here's an important fact that I maybe should have mentioned. Well, I didn't have time to mention it last time. Fact, the Riemann mapping we constructed, the mapping we constructed in the proof, mapping F from omega to the unit disk that we constructed in the proof of the Riemann mapping theorem. That's the mapping with the biggest possible derivative. With f prime of a equal the max. Remember I showed it, I called that the soup, but it's actually the max because it's assumed. So that's the max of h prime of a, such that h is in my class of one-to-one analytic maps into the unit disk, is such that f of a equals 0. Has to be. So, and the y is easy. Oops, sorry. The y is easy. I've kind of seen something like it. Suppose f of a is equal to the f that we construct. Suppose f of a is equal to b, which is not the unit disk, which is not the origin. Well, then I've got this picture. I've got my omega. My A simply connected, so there's no holes, and I map to the unit disk. It's one-to-one onto the unit disk. Let's see, and it would map. Here's the origin, and A would get mapped to some B. Here's F. And of course, I know a one-to-one onto map I can move B to the origin by composing with the Möbius transformation. Okay, so this mapping would be, let's call it phi sub B of Z equals Z minus B over 1 minus B bar Z. I claim that that would have strictly bigger, when I do the composition, it would have strictly bigger. So let's let F of Z be equal to phi sub B of F of Z. I claim that that has a strictly bigger derivative at A. So F prime of A is strictly bigger than little f prime of A. Okay, this is a square F. And that it just can't be. So that F, remember, was the max, so it can't that can't be true. And the calculation is easy. You calculate f prime of A equals phi prime of f of A. Well, f of A is B. And we multiply that times f prime of A. And this thing, when you calculate it, is 1 over 1 minus B squared, modulus of B squared. And let's see, what is that? That's bigger than 1. So I guess that's a because. Okay, so we're getting closer to realizing we kind of have the Riemann map. And so a question now that is natural. How many maps assume that maximum? So, yeah, how many maps? In script F, assume that max. Derivative at A. What's your guess? Yeah.
Infinite, probably, if you can pull some of the rotations.
Yeah, exactly. They're unique up to rotations. The answer is Riemann map is the F is unique up to rotation. And in fact, I think you had a homework problem where you showed that. So let's see. It's the Schwartz. It's a consequence of Schwartz lemma. Let's think. Let's suppose I had two Fs. Both Riemann maps, the ones you get in the proof. Riemann maps for A. Well, then if you go backwards by one and forward by the other one, we know they have to take map A to the origin. So then, for example, F1 composed with F into inverse is a map from the unit disk to itself, and it fixes the origin. Fixes z equals 0, and it's 1-to-1 onto. And so, of course, we know that's a rotation. I proved that back in some lemma early on. It's the let's see, it has, so that derivative f prime is, let's call this f. Or let's call it capital Phi. Okay, so for example, I would have f prime of 0 is less than or equal to 1, and f inverse prime of 0 would also be equal to 1. So f inverse prime at 0 would also be less than or equal to 1 by Schwartz lemma. And this is equal to 1 over phi prime of 0. So phi prime of 0 is equal to 1 in modulus. And Schwartz implies that it's therefore a rotation. Where lambda is equal to 1 in modulus. Okay, so the fact is, so we conclude that f1 of z is equal to e to the I theta times f2 of z. Okay, so that if I just have one Riemann map and take all the rotations of it, I get all the Riemann maps. Okay, and in fact, so if I want to make it unique, to get the Riemann map, play around with the right e to the I theta that makes the derivative a real thing along the real line, positive real line. Take a Riemann map with f prime of a on the positive real line. And you just get that by multiplying by e to the I theta to rotate it around so it's in the positive real line. Okay. So the fact is there's a unique I guess you'd have to say I have the Riemann map associated to the point A. Given A in omega, which is not the whole complex plane, simply connected, there exists a unique analytic f from omega into the unit disk that's one-to-one onto with f of a equals 0. That goes, they always satisfy that by my remarks. And f prime of a is in the positive real axis. So sometimes you'll see the Riemann mapping theorem with some more details like that. That finishes off the Riemann mapping theorem. Any questions about it? Well, let's see, I should make some... we're not going to do these things, but you might ask, what if omega has holes? Then there's kind of a version of Riemann mapping theorem. So let's see, here's the 2 connected. So omega is 2 connected. meaning one hole. It means there's two boundary components. Then here's a two-connected domain. It has one hole. It's called two-connected because notice there's two boundary curves. Well, then the famous theorem in this case is that there's a map to an annulus. Okay, let's call this little r and big R. So every two-connected domain is conformally equivalent to an annulus. And a fascinating thing, it's not just any annulus. A fun fact is that if two connected domains are conformally equivalent, then the ratio of those radii have to be the same. Fun fact, if two connected domains are conformally equivalent, and of course it's proved with pure complex analysis reasoning. You know all the basic facts, and we could go through it, but I don't want to go through it. It takes too long. If two connected domains are conformally equivalent, then R1 over R1 has to be equal to R2 over R2. That's called the modulus of a two-connected domain, and it's an invariant under biholomorphic mappings. So there's some pretty interesting stuff going on when you start having holes. And the automorphism group of an annulus is incredibly much smaller than the automorphism group of the unit disk. So there's going to be rotations, obviously, but there's only really one other automorphism, and that comes from an inversion type map, taking 1 over z. So I could take 1 over z and then adjust so the radii get mapped to the right thing and get an inversion of the annulus. It would map the outer boundary to the inner boundary and the inner boundary to the outer boundary. So it's interesting that the automorphism group suddenly starts getting small, which is why you can't do as much when you're doing conformal mapping in regions with holes. They're way different than simply connected domains, where you have all these automorphisms and transitive automorphism groups, etc. It's a different ballgame. And in fact, in higher connectivity, let's think about the n-connected case. Okay, so I'll say in the case of an annulus, lots of automorphisms. You'd have e to the I theta z, just a rotation, and something like n1, like a 1 over z, called an inversion. Maps the inside curve to the outside curve. Okay, but not as many as the disk, but not as big. In particular, it's not transitive. As ought D10. In particular, is not a transitive group, meaning you can find an automorphism that maps one point z to a given second point w. Okay, so let's talk about the n-connected case. Okay, an n-connected domain would have, let's see, that's 4 connected. There's 4 boundary components. Then the kind of a Riemann mapping theorem for this picture is that you could map this to the unit disk with circular slits. So I could have 1 circle, 2 circles, 3 circles. Those are circular slits. Okay, there's a total of 4 boundary curves there, so that's the right thing. This is a 4 connected. And so this would be 1-to-1 onto analytic. So conformal. That's an interesting fact. Another version, you can map to an annulus with the right number of slits taken out of the annulus. And so now you'll think, well, what the heck could an automorphism be of that, something like that? And you can come up with cases where there's very few automorphisms, like maybe something like plus and minus z are about it, or maybe some rotations or some very... The automorphism group actually becomes finite. So that's the fact. Can equal just the identity map. F of z equals z. Could be the only automorphism. Or finitely many simple automorphisms. Can be just the identity map or finite. In fact, if you ask yourself what's the most common thing it could be, the most common thing it could be is the identity map. If you just randomly pick something, chances are it's the identity map only. Okay. So that sort of limits the usefulness. And you can come up with numbers like the modulus in the annulus case that's simple to do, R1 over R2. In this case, you'd have those slits, the radii, the arc length of the slits, a whole bunch of numbers. Those are called moduli, and they're invariant under... You can show that there's combinations of them that are invariant. So it's a fascinating subject. Conformal mapping of multiply connected domains. Let's see. I thought I'd review something since exam's coming out this afternoon. Was there any questions about this stuff? Here's a review problem I meant to do. This was a problem on one of the homeworks. I want to find integral from 0 to infinity of dt over 1 plus t to the 5th. This was a homework problem. And I gave you the contour to use on Piazza for that thing. But let's say I didn't give you that. And you might ask, if I want to integrate along a piece of pie like this, let's call this C sub r. Let's call this the bottom, let's call that the top. And let's call this angle here alpha. Of course, the integral along the bottom is the integral I want. This is 0. This is r. Okay, so the integral along the bottom is the integral I want. And let's see what the top here, if I'm going to calculate the integral along the top, I'd take minus top. That would go from 0 to this spot right here, which is r e to the I alpha. So minus the top would be parametrized by z of t equals t times e to the I alpha, as t ranges from 0 to r. And I got to find an angle so that that's going to be related to the integral I want. And so let's see, the integral along t then would be minus the integral around minus t. And see, what's the z prime of t? Z prime of t is e to the I alpha. Of my 1 plus z to the 5th dz. That's going to be minus the integral as t ranges from 0 to capital R over 1 plus, okay, this is t e to the I alpha to the 5th. And then the z prime of t is e to the I alpha dt. Okay, so that's equal to minus e to the I alpha times the integral from 0 to r, 1 over 1 plus e to the I 5 alpha t to the 5th dt. And so if I want to get something related to my integral I want, I would like to have that alpha be such that e to the I 5 alpha equal 1. Then it would spit me out something related to the integral I actually want. And I can use the residue theorem. So let's see that I could get that if I had 5 alpha equal to 2 pi. Here's a good choice. Five alpha equals 2 pi. In other words, alpha equals 2 pi over 5. Okay. If I use the Pac-Man, let's see, I don't know what would happen if I tried to use the Pac-Man integral. It might not. I'd have to think about the Pac-Man integral. I'd have a whole bunch of poles to deal with. I'd have 5 poles to deal with if I went all the way around. But I don't want to do that. This is much easier. So that's why I gave you this contour. When you have this alpha being 2 pi over 5, then there's one spot here where the pole occurs, which is at e to the I pi over 5. And then you can use the residue theorem. Okay, and so you get, when you do the residue theorem, the big thing is to show that the integral along c sub r goes to 0. let's see, that would be less than or equal to 1 over r to the 5th minus 1 times the length, which would be 2 pi over 5r if r is bigger than 1. Of course, that goes to 0 as r goes to infinity. And so you get, let's see, so when I take the limit here, I get the integral along the bottom is the integral I want. So that gives me a 1 here. And then I would get the minus e to the I 2 pi over 5 times that would give me the integral I want. Integral along c sub r goes to 0, so I'd get a plus a 0. And when I take the limit, and then I'd have 2 pi I times the residue at e to the I pi over 5 of 1 over 1 plus z to the 5th. And that has a simple pole at e to the I pi over 5. And so the thing on the bottom has a simple 0. And that's one of the easy cases to calculate a residue. This would be 2 pi I. Let's call this f of z equals 1. G of z is this thing on the bottom. This is one of the simple cases to calculate the residue. This would be f of a over g prime of a, where a is equal to e to the I pi over 5. And that g is 0 there, of course, but its g prime is not 0. And so, in fact, this is going to be 2 pi I times 1 over g prime would be 5 times e to the I pi over 5 to the 4th. And you can play around with that. Let's see, what does it turn out to be? 2 pi. Oh, look, there's a 2i there. That's equal to, I like the pi over 5, I'll pull that out in front. Then I have 2i over e to the I 4 pi over 5. That can't be right.
You need to divide over this stuff too, right? If we're trying to calculate the answer.
What am I trying to do?
There's some constant on the left hand side, right?
Oh. Yeah, okay. Duh, yeah. So the integral I want is 1 over 1 minus e to the I 2 pi over 5 times, I'll pull the pi over 5 out in front. And then I would have this times 1 over e to the I 4 pi over 5. Let's see. I think I'm going to multiply. Oops, there's a 2i somewhere. It's right here. And now I think if I multiply the top and the bottom by e to the minus I pi over 5, would that be smart? Yes. So if I multiply by e to the minus I pi, or minus e to the minus pi over 5, and when you do that, you'll get pi over 5 times e to the I pi